Let's do this. All right, so this is Kalman Filters. It's gonna be a good time. There's some math, but just stick with me. I promise I'll explain it in English. Okay. So first thing we need to worry about is basically why do we even need Kalman filters? And there's a bunch of different reasons for them. Oftentimes they're used for object tracking, and that's really what we're going to care about using them for. And so, like in computer vision, for example, that picture in the top right, you can see, that's tracking birds over the course of time, or a bird. And then this graph I'm going to come back to later. Actually, that's tracking object in 1D. And that's pretty much just where we'll start, because today I'm going to go over some theory, and then theoretically next week or the week after we'll do a little coding thing. But it's too big to do all in one, so I don't want to overwhelm you guys. So basically, what do they do? And again, I'll use our context. So given a problem, so we're given a system with sensors, and then for a Kalman filter, specifically just a plain old Kalman filter, we're going to assume that the system is linear, and then we're going to assume that the sensors have Gaussian noise. So that means not, they do not have non-Gaussian noise. And for those of you who don't know, Gaussian noise is basically what you see right there. It's like a bell curve, meaning that the sensor predicts, let's say, our location, and it's just as likely to predict it wrong to the right of where the real location is and to the left of where the real location is. So basically its inaccuracy is just as likely to be to one side as it is to the other. And when there's biases introduced, this is when it becomes nonlinear and then introduces some other issues. So the Kalman filter proposed solution, which is actually kind of cool. So it uses the previous state of the system. So basically, hey, this bird's flying this way. Where was the bird just recently? Okay, so I only need the last state. I don't need all the ones before, which saves a lot of memory, which is great. So where was it previously? And then where is the sensor saying that it is? And so it combines those two inputs in and basically gives you sort of a weighted output. And it attempts to eliminate the noise from the sensors, because that's something that is quite important. If you ever use sensors in the real world, they don't give you a 100% accurate prediction. They usually give you some noise, and this can be a big deal. And so let me see if I can get this to go. Here we go. This is a really good example that I told you I'd come back to this graph. So the blue is the measurements. This is basically the sensor, and you can see how noisy it actually is. Now the real track, meaning where the object actually is the green, and you can see that the red is basically what the Kalman filter is doing. So it's basically going to say, hey, I don't know if you can see my mouse. I hope you can. But if so, around 20 here, okay, you can see that our green line's right here, our red line's right here. It spikes up all the way to up here for the sensor. So the thing is that if we were actually tracking this, we'd be like, whoa, the velocity of this object just got really high. But that's actually not what happened. So you take a weighted output to kind of mediate that, and it works out really well. So you can see the red line does a pretty good job. So this is a little bit of math, but these are just the 8 parameters you need. You need 8, and then you're done. Okay, so just stick with me here. They can be basically split up into 4 and 4. So there is the process model and there's the measurement model. The process model deals with the past state. Measurement model deals with the sensor. So like I said, there's 2 inputs, your past state and your measurement. So just real briefly, I'll go into them again, but just real briefly, the F is your state transition matrix. So basically the state that you're in currently. B is your control input matrix, which oftentimes is your velocity or something like that. And I'll show you that. But more importantly is this Q, and later on I'll show you this R. These are basically when you hear people saying, I'm going to tune a Kalman filter. It's the same idea as tuning a PID controller. These are basically what you're worried about. The covariance matrix, for our purposes, is basically just the variance of the noise. So remember how I said earlier that the noise is just that Gaussian noise, because we're assuming it's Gaussian. So basically, how wide or how skinny is that Gaussian curve? And so that's basically what you're tuning, because the covariance matrix tells you the variance of the variable, but then it also tells you how much 2 variables vary together. Okay. So in our case, we'll have like X, Y, and Z. X, Y, and Z won't vary together because, as you know, spatial dimensions are completely independent of one another. So because of that, all we have to worry about is just the variance of Z, the variance of Y, and the variance of X. So that's basically what these Q and R are. One of them is for the process, which is your past state. One of them is for your measurement that you're getting out of the sensor. And so then there's these other things that I'll show you, control input vector, the initial state, the measurement, you know what I mean? And then here's your measurements from your sensor. But I'll show you those in a second. The ones that I explained are sort of like the main ones. Q and R are really what you need to remember, okay? After this slide, I'll ask you guys have any questions or anything like that. So these are the two models I talked about. Here's your parameters over here so you can cross-reference. There's two main equations here. So x of k plus 1 is basically saying, okay, where am I about to be? Where is the next state? I'm predicting where I'm going to be. So we're going to take in our state transition matrix, okay? And then we're going to multiply it by where we're at right now. So the state transition matrix, I'll show you an example of it. But this is basically all going to output where I think I'll be. And so it takes in basically the control input, which is oftentimes like the velocity, and it takes in the past state, and then it adds on to it the noise. So W of k is basically what I described earlier, that Gaussian curve, and Q is the variance of that curve. So that's what I said on the last slide. So W of k is connected to Q in the way that Q is what you're tuning. Same goes for down here. This is saying, okay, what do I predict my next measurement to be? And this is based off of the measurement matrix times where I was last time. And then we're going to add in V of k, which is the same idea as W of k. It just uses R instead of Q. And so these are your two tune parameters, R and Q. So far, does anybody have questions? I'm almost like afraid to ask, but like, let me know if you have questions. I don't mind. This is a lot.
So Noah, I do have a question.
Sure.
And it's not everything that makes complete sense to me so far. My main question is, have you substituted in another name for a priori and a posteriori?
What do you mean?
Like you have your prior measurement and your post measurement.
Yeah. So like that would be down here.
Okay.
This is your new measurement based off of where I just was.
Mm-hmm.
You see what I'm saying? So I guess what's your question?
Yeah. So my question is, where is your a posteriori and your a priori measurements? Are those what you're calling the process model and the measurement model?
Yeah. So it'll make better sense whenever I do. Whenever I do this. This is like the main algorithm,
Okay.
and so this is going to be basically your predicted state, and this will be your updated state. This will sort of be, you know, where I am, where I'm about to be, if that makes sense.
Yeah. Sorry, I'm just like every time I've read about them before, they always use those two terms. So that's what I was familiar with, and I was just seeing like how to relate that to this. But yeah. Thank you for explaining that.
Sure. Hopefully it'll make more sense as I go along. There's like depending on who you talk to, there's different terminology for this sort of thing, but they all connect the same way. So before we do the algorithm, I'll just mention again that Q and R are your noises, and they are not known. Okay, so they must be tuned. And there's a few like tips and tricks that we won't worry about this week, but there's a few tips and tricks on how to choose your variances. And so, like I said before, the covariances are often just zero. So all you're worrying about for Q and R, because those are covariance matrices, you're just worrying about the variance of each variable, not how they vary together. Because X, Y, and Z are spatial dimensions. They're completely independent of one another. They don't affect one another, at least for our sake, because we're doing object tracking. So this is the algorithm. 2 stages, just like we had a process model and a measurement model. This is again broken down into 2 parts. There's your prediction and then your update. So I'm not going to go too deep into this, but what I am going to show you, because basically it's sort of like a pig controller where once you set it up, it's just a matter of tuning it. It's good to understand what's going on, but when you see an example on the next page, you'll see that it's really not it's not that bad. It's just setting it up, and then after that, the tuning is just those two parameters, Q and R. So first thing we're going to do is we're going to calculate. I showed you this calculation before, so you're basically just saying, okay, here's where I just was. This is like my velocity, for example, or my acceleration, depending on what's going on. And this is basically, okay, this is where I predict that I'm going to be. Okay, this is where I think I'll be in the next state. And this, which is actually kind of interesting, this part is saying, hey, I know that I'm going to be a little bit wrong. I'm basically just using where I just was to predict where I'm going to be. So that's just, it's not going to be 100% accurate. So it's going to use this Q, and then it's going to try to predict this thing that's called P. It's using the straight transition matrix and basically how wrong you were last time, in addition to how this like Q parameter, it's going to blow this up. Okay, so it's going to be like a predicted error covariance. So how wrong do I think I was? And this is going to be a large value at first. Okay, after this calculation. So prediction model, where do I think I'm going to be based off of where I just was, and how wrong do I already think I am? Okay, so then over here in the update, we're basically going to correct using the measurement for where we're actually at. So we're going to take in our measurement, which is Z of K. Okay, and that's shown down here, number 8. So we're just saying, take in your measurement and then take in the measurement matrix times X of K. Now, all that is basically, if you remember, we calculated this X of K earlier, okay? And H of K, the reason H is there is because oftentimes X of K is includes all of the parameters that we did over here, both your position and your velocity. So the only thing that we're tracking here with the sensor, like in our example, would be the position. We're not, in the example I'm going to show, we're not predicting the velocity from our sensor. It's just our position. So we're going to multiply this transition matrix, which is literally going to be like a 1 and a 0. And the reason that is because we're just extracting the part of X of K that includes position, because we don't want to worry about velocity, because Z of K doesn't contain any velocity. So that's a long-winded way of saying that Y of K here is just going to end up being what our measurement is minus the predicted position that we exist. This H times X of K is predicted position. So this is the magic right here, this Kalman gain. This is where you're basically going to weight your outputs, basically saying, how much do I trust the measurement versus how much do I trust my past position? And so it's going to take in all these different things that we're not going to really worry about right now, because it's really just going to get too far down the rabbit hole. But it's basically going to take in R, which, if you remember, that was one of the covariances that we said, okay, this is how much the noise of the measurement is. And it's also going to take in this P. Hold on, my thing keeps going away. Here we go. And it's also going to take this P minus K, which you remember depended on Q. So this is where your tuning of P and K really come in. And it basically tells it how much do you want to trust the measurement versus how much do you want to trust where you just were. So then after that, all that Kalman gain's used for is to update where you actually think you are. So it's going to take in where you predicted, then it's going to multiply the Kalman gain by this, which, if you remember, was just your measurement minus where you thought you were. So they call that like the measurement residual, sort of. And so this is going to be an update of where you think you are. And then this is just taking in the identity matrix, which that's all that I is. But basically, it's going to take in the Kalman gain, the measurement matrix, and the variable that you calculated over here, and update that. And then this is just now how wrong you were, or at least how wrong you think that you were. This is like saying, okay, I think I'm going to be this wrong. This is saying, based off the measurement and the past and where I just was, this is actually how wrong I believe that I was. You never know for sure because you don't have true data, but this is a more accurate representation of how wrong you really were from this one. So if you actually look, this P plus here, that just means it's updated. That's the plus. It actually ends up going back into here, and you use that later to calculate your next P minus K, which is your new how wrong do I think I am. And so these arrows right here, I put these here because all this is a loop. This is literally the 6 lines of code that will be the Kalman filter. You're going to end up just calculating your prediction, then calculating your update, and then these two right here will just feed right back in, because you can see X plus goes right back into here and P plus goes right back into here. So it's just a constant loop, and that's how the whole thing works over and over and over again. So for like an example of this, which hopefully will tie it a little bit better together for you, this is a 1D example. So no 2D, we're just basically traveling along an X line. So your state vector, okay, is just going to be X of K and V of K. Like I said before, you have both your position and your velocity. So you'll actually recognize these are going to be your equations, which you'll set up your equations for how your object is like predicted to move, basically. And for the most part, they're going to be the kinematics equations, as you'd expect. So that's what these are. You saw these in like physics 1. X of K plus 1, which is your new prediction, which this right here is this equation. Okay, so this is the first step in the model. So you're basically just going to take in this, and for those of you taking like linear algebra or something like that, or know anything about matrix math, these two, F times X of K plus this times A, this whole equation just equals these two equations. Okay, so it would end up being the same thing, but you're just breaking it down so that you have it in the form of this equation. Okay, so this will be your F, this will be your B, and this is why I said like U and B, these are like your control input. They're sort of like difficult to explain a little bit, at least for me, and they're basically just, in this case, your acceleration. Okay, so that's sort of like something that sometimes is constant, sometimes can change. That's why they call it like the control input. And so then your Z of K, your measurement vector, is just going to be H times X of K, which you'll end up seeing up here, H times X of K, and that's your measurement residual. And then that's just going to be, like I said, a 1 and a 0, because all we're doing is we're extracting out from X of K, which is both the position and the velocity. We're just extracting out the position. So we don't care about, that's why there's a 0 here. We don't care about the velocity because all our sensor is measuring is position. So that's just going to be our new measurement. So this sets up this, okay? And you can, like, if you look at this, you can see that this would set up everything to end up doing the whole algorithm that was on the previous slide. The only thing you're gonna have to add in is both your Q and your R. And those are just tunable parameters. And then everything else can be calculated from here. Okay, so this is literally all the setup that you need to do for a 1D example. For a 2D example, you'd add in, there would be 6 parameters, I believe. You'd have, instead of just X of K and V of K, you'd have X of K, Y of K, then you'd have like your yaw. Okay, so like the angle that you're going at, and then you just have the derivatives of each of those, meaning that your velocity in X direction, your velocity in the Y direction, and then your angular velocity. So that would be the only difference. It would just be a larger matrix, but the same idea still holds. So once you grasp this 1D example, it pretty much just all not falls into place, but it's easy to extrapolate from there to do your 2D example, and then from there your 3D example. So does this make any sense so far? Because this is the bulk of it. Okay, so like after this, it just goes.
Yeah, I had a question. Since this model seems like it's built for like kinematic motion, would something be possible for like a different like sensor measurement? Like say you have like a temperature and you're trying to see errors, would you just have to change the state variable, or?
Yeah, so the thing that you would change is like exactly like you said, this state vector would completely change. It would depend on what you're measuring. This is just the common setup for that, but actually all the way back here, these are like the top 3 things that Kalman filters usually use for it. Just like you said, temperature, economics. Economics is a very like broad term, obviously, but there's a lot with finances people do for predicting the market and tracking it, and object tracking. So yeah, you can do it. Your equations would just simply be different. You'd have to look in that. I actually don't know what the equations would be here, but your Q and R would be the same situation. You just vary those just like you would any other Kalman filter. So it's really just setting this up.
For temperature, I'm guessing that there's like a handful of different options you could pick on there, even based on like, obviously there's more than just those kinematic equations that you just put in there. There's like other factorings of those and for temperature and stuff. So
Yeah,
it's
yeah,
kind of like your, like whatever fits the purpose of your, whatever you're trying to filter and measure, I'm guessing is like what is going to go into that state vector from my understanding.
yeah. That's my understanding so far too. I looked at a few like economics ones, but like I don't know, economics was sort of like above my head, but it was basically like that's the part that people often vary in their research is they'll change these equations in the same way that we would change a loss function, because this is basically determining right here what your process model is going to see. Your measurement model, you know what I mean? That's that doesn't matter. Your sensor is always going to be the same, no matter what sensor you have. You know what I mean? It's just going to output what it outputs. It's really this that's going to change along with your Q and your R. But once you get that set up, then you're good.
So choosing the state vector kind of like determines your application in a sense of like what you're applying the Kalman filter to, and then you have your oof, man, it's like on the tip of my tongue. Sorry. Then you have your Kalman gain, which is also like user defined, and it's like also kind of like application dependent based on how you want to weight your inputs. Correct? Like those are like both things that are like the state vector and the Kalman gain are kind of like user interactive where you want to tune those kind of accordingly.
Yeah, generally you're going to end up like with motion, you're generally going to end up using these as I understand. So I'm sure for like possibly temperature and when whatever application you're going to use, you're going to try to use the standard equation sort of like this, like whatever the kinematics equivalent is to temperature or something like that. But yeah, Q and R, the quote unquote user interactive part, it's if you ever tuned a PID controller, it's similar to that. It's the same idea. You want to start like, not too high, not too low, but then from there you'll just vary until you can get like a result that seems to fit best. So yeah. So this is the summary. And basically I'm going to explain to you why we can't use this. So the great thing about Kalman filters and the reason that people ended up just doing extensions of them is because there's a lot of benefits. And one of them is being that it just uses the last state and measurement. So it only takes in two things, the measurement, which has its external power, and then you can just basically just use any grade A sensor for it. And then it just uses the last state, which it did from the math that we predicted. You know what I mean? It was like, I believe the fifth step. And so it doesn't need to see everything before that to try to basically then predict your new line or your new position based off of the previous line in a 1D example. Also, it just uses Q and R as error. Okay, so then you can just tune those to be whatever ends up fitting best. So it's a simple idea, sort of like a PID controller, because that's probably the most analogous thing that I can think of. But the problem is that it only works if the equation is linear. Okay, so your like original like kinematics equation, let's say, is linear, and it only works if Q and R are Gaussian. So here is basically why our equations won't be. So you probably heard before that the world isn't linear and the world isn't Gaussian, and here's basically why. So in real world applications, let's say if I have a camera that's facing straight forward and my object is straightforward, I'm fine. That'll be linear. But if my object is now off to the right a little bit, in order to calculate that in the same way that you did like projectiles sort of in physics 1, now you have that angle in order to calculate its distance. Okay, as soon as you introduce angles, that's immediately nonlinear. Okay, and there's tons of angles within measurements, and that's sort of where that is one area where it starts to go nonlinear. Okay, and then on top of that, Q and R aren't going to be Gaussian because in crowded environments, or in an example where, let's say, like a green tennis ball passes across a green background. Let's say that our sensor is computer vision, because that's a popular use case for us. if the background, which is also green, let's say, ends up being misconstrued as part of the ball, okay, so now that means that my ball, I'll use a Rubik's Cube as an example, okay? Now my Rubik's Cube is no longer just this size. It actually thinks it's a little bit bigger on this side because it predicted part of the background as part of the cube. So now the location of the center point where my cube is now not going to be just as likely wrong to the right as it is to the left. It's always going to be biased this way because it thinks that there's actually an additional part right here. So my noise is no longer Gaussian because there's a bias. And the same goes for like a crowded environment. So like down here, this guy who's labeled as 129, instead of there being two bounding boxes here, or I think it's a woman actually, that's bad, but she could get misconstrued as this guy right here, and her bounding box could grow. Now her center point's going to be biased to the left. So now you no longer have Gaussian noise. You no longer have that bell curve. It's actually skewed one way or the other. So the point is that the Kalman filter idea can still be implemented. However, we need to extrapolate from that. And so that's where these two come in. And I'm just going to leave it at one slide for these just because they get much more in depth in the math, but I'll give you the overarching view. So both of them deal with nonlinear problems like we described, okay, with non-Gaussian noise. Basically what they do is they just linearize the problem, which you've done in a lot of your calc classes, probably, but if you're like me, probably forgot them because who wants to remember calc? And then basically in the extended Kalman filter case, which you've heard a lot, you've heard people say EKF or throw that term around. It linearizes by calculating the Jacobian matrix. Point is it basically does this by approximating the mean, okay? And so from there, this is a really good picture actually to view it. So you have your nonlinear function, and it basically tries to take a nonlinear output, which is going to be this, this red line, or what it's calculating, okay? And then it's going to try to fit a Gaussian to it. So you're going to get a non-Gaussian output and a nonlinear output, but you're going to try to fit it to the closest possible Gaussian linear output that you can. And then from there, now that you have a linearized problem, you can just use the Kalman filter just as we described before. So there's just a step before where it does some matrix math, which actually isn't that long. Generally, it's like 4 to 5 lines of code, two of them being really significant and the other 3 just set up. And then from there, you can just predict your actual output. In the unstinted Kalman filter, this is basically supposed to be better than the extended Kalman filter, okay? And this is like a more recent version. So a UKF, if you want to call it by its acronym. Same idea, nonlinear problem, linearizes it, but basically the way that it's explained best is that this in the EKF just predicts the mean, and then from there tries to linearize it. So basically, if I asked you, do you think that you could find me a more accurate line if I gave you 1 point on that line, or if I gave you 10 points on that line? And without thinking, you'd come to the conclusion that 10 points is going to be better. I'll be able to better fit the line. 1 point doesn't really give you that much. So that's basically what the UKF tries to do. It gives you what are called sigma points. And one of these sigma points is always the mean, just like you get at a UKF. So you get more points out. And then each point is actually weighted, basically telling you, okay, how important is this point to calculating the overall Gaussian fit. And so it does the same idea as this one. It just takes those points in, one of them being the mean, and then tries to fit a Gaussian curve to it. Okay, or like, as you can see, it's like an approximate Gaussian. So basically this one approximates it better than this one. The problem is that this one is more computationally expensive. And oddly enough, after looking at a few papers that have done research on this, generally the EKF, even though you're only getting 1 point out of it technically, you're only getting the mean in order to linearize it, it generally does near as good a job as the UKF. So this one might be worth looking into, but generally EKF is accepted as a pretty good solution to the problem. And obviously there's other filters like the particle filter and stuff like that you've probably heard of, but the EKF generally gets the job done at a low low computationally expensive output. So that's basically what we'll probably end up using for our application as an EKF, because we live in a nonlinear, non-Gaussian world. And then we'll just be able to use the exact same equations that we saw earlier. Okay. And then we'll be, that'll be it. It's literally just extrapolating it to 3D. Okay. So ask me questions and also enjoy Bugs Bunny because he's the best of the characters.
Dude, awesome presentation. Thank you so much. Here's some physical applause.
Wow, I feel like I'm in person now.
Yeah, dude, thank you.
Sure, I know it can be complicated. It took me a while. It took like hours of videos to really understand this. So like I'm cool with questions because it can get weird.
I just also shared two great resources that I've like. One Nayana shared with me when she was researching at CMU this summer, and I know that she like made an implementation of a Kalman filter based off of this paper. And then I also included a paper that's on. It's like much more of a review paper, so it's a super long read, but it covers a ton of different linear Gaussian models and kind of gives you like a theoretical overview of how those are working to like accomplish these types of tasks.
Sounds cool.
So Noah,
Sure.
so the EKF and UKF, those are basically almost like pre-processing steps. And then after you do that, then it just throws it into regular Kalman filter, like process or I guess stack.
Yep.
And it's just treated like normal.
100% accurate. That's exactly it. It's basically saying like these EKFs and UKFs basically say, okay, it is too hard to deal with a problem non-linearly, so we are just going to linearize it and then just use what we already know. That's literally what is happening.
Okay, and does the EKF step have to be, the EKF and UKF steps, do they have to be done every time you get new sensor data, or is it done just at the beginning?
It is done
Yeah, it's got to be
just at the beginning, because after that, the non-Gaussian part can just be simply dealt with these Q and R variables. I actually want to look into that because it makes sense that you would only have to do it once. But I am hesitant to say that only because that, you know, if I'm wrong, it's more costly than if I was wrong the other way. So I'll post something in the chat about that. That's a good question.
Okay.
I believe that it's linearizing it like via each iteration, you know, like every reading it's taking, it's got to like linearize that in some fashion. And I'm pretty sure that in terms of the EKF, that it's actually using a Kalman filter to like in the EKF to, it's like using like a, what would you call it? Like a virtual Kalman filter inside of it to find like that mean or like the median value that's being output. If that makes sense, like a nested Kalman filter type ordeal.
Yeah, in order to find your F in the EKF, ultimately what's just going to happen is this F now needs to be calculated differently. It's calculated by finding like a Jacobian matrix of it. And so that's what you'd end up doing. And actually, Adam, it makes more sense that that Morgan would be right, that it does have to be calculated each step, because this unscented Kalman filter is widely known as more computationally expensive. And the only way that would be true is if you had to calculate it every single time. If you only had to calculate it at the beginning, you know what I mean? It wouldn't make that much of a difference. So yeah, I would bet that it would have to be done every step. And one thing that I want to say before Tom stops the recording, but by the way, you guys keep asking questions, but one thing I want to say is that this, like the reason we need to do this like one more time is because like, and the reason we need to track cars is basically so then we can figure out like their velocity. Okay. And the reason for doing that is because if you think about when you're driving, you're not driving based off of where cars are currently, you're driving based off of where you think cars will be. You know what I mean? So if a car is like this close to me and I'm parked, I'm not that concerned. But if a car is this close to me and it's driving toward me, then I'm concerned. Okay. So that's basically why we need to track objects, just as a general overview.
We don't want to be merging into a lane where a car's going 10 kilometers faster than us and then just get rear-ended. Yeah.
There's some cool research right now on speed estimation and depth estimation based on like parallaxing, like watching like a car and differentiating that object from its background and kind of correlating the speed between those two. But I still think that you couldn't do any actual tracking with that method. You know, it would just give you a speed metric, whereas the Kalman filter can give you speed and like this like spatial position, which makes it like especially valuable.
Yeah, and also one thing to note is that the way that you have to test these often is by giving it like true data, because that's what this graph says. Like technically at no point do you know that you're correct. There's no verification happening. All you're doing is a weighted output. All you have is your measurement, which is the closest thing to real data that you have, and your past measurement. You never ever know the real track. That's why this is so cool. It's never going back like a neural net would be and saying, okay, how wrong was I actually? It's doing that by referencing what it predicted based off of the process model with the measurement model, but it never ever gets to reference the real world. So that's why it's cool that over time it can stay so close to this green line, which is ultimately the real track. So in order to test these, you often have to give it like real data in order to, you know, guarantee how right it is. But that's what's really cool about it. It never has to reference back to the real world. It can just use those two parts to do it all by itself.
And so going off of that, I just have two things. So that means that you'd have to hand tune those Q and Rs, right? Because it doesn't know what the real data is. You would have to almost have a visual output like this and then run it through, you know, many iterations and then just kind of each time tune Q and R to get something that's
generally
more exact.
There's research papers just on the best ways to tune Q and R. Generally, like this is a very, very like general rule. So like it's not like don't just do this, but you don't want to make it too big, but you generally want to start bigger and then bring it in closer. You want to think that you're going to be really wrong and then bring it in closer. You don't want to start off with like a really small Q and R, because then you're just gonna it's not going to give you data that's going to be meaningful to tuning it later. Yeah, so that's a general rule.
Okay, and then the second part of this, so this is very important for, I guess, probably state or, you know, state estimation, right? So would this all be thrown over to Matt and
after talking with
there?
Nick and Andrew, it seems like this is a beginning of the state estimation stack back of the perception stack, and I think we can determine who's responsible for it. But it sounds like since the state estimation and us will start to merge closer, you know, as we get closer to like integration, it sounds like there might be some of us working on this in addition to some of the state estimation people working on this. Like, you know, from Nick's point of view, it would be nice if we just gave them, and he didn't say this, but like I'm just saying from a state estimation person's point of view, it would be nice if we just gave them the Kalman filter. But then from our point of view, it'd be nice if they just did it. So the point is that you could technically do it either way.
So I don't know very much about like what's been going on in like the backdoor conversations about this, but I was under the impression that like the Kalman filter specifically is something that's been implemented like a bazillion times. Like for example, Kalman filter is just built into ROS. I think there's like a handful of different Kalman filters and EKFs in ROS. And I think the biggest task for either state estimation or perception is going to be like the tuning and whatnot task versus like actually making one of these from scratch. It's going to be like we find like one that's like super optimal that's like built into ROS, and we just have to like do this process that Noah just went over, like get some like ground truth info and tune our stuff. But yeah, still I don't know like which sub team that would like what work who that would get assigned to, but I don't think it necessarily is basically it's not doing it from scratch, you know, like you can just like try a bunch of other Kalman filters with the data that we're going to be getting, is my impression.
That's completely plausible. That'll be something I guess we figure out as we get closer to that, which is nearing, you know what I mean?
Like kind
so,
of
yeah, you could be right.
What we're doing with these like evaluating these other networks at the moment and stuff is like we're taking a ton of stuff that's like working out of the box and making sure that it works, and then we're going to like fine tune it towards our data like once we get data sets and stuff. And I think even like maybe if like the one in ROS isn't super proficient, I bet we can find a Kalman filter that's like online where, yeah, I don't know, like we just have to do the tuning element of it. I might be completely wrong about that, so I don't know.
That's good. Okay. I mean, if anybody else has any questions, let me know.